Well, that thing is running for a variety of circumstances and variety of operating conditions. So even if it's the best design at the nominal conditions, baseload, etc., it needs to perform well and not break and not violate the criteria that it has and the constraints on where it needs to operate for all of those other spaces, all those other design points. And that could be thousands of points. So no one wants to simulate thousands of extra just to be safe, right? Let's make some surrogates. And then maybe in other use cases we've seen, you can get basically a 5-to-1 ratio when you explore this sort of CAD sensitivity, reliability, and robustness space. You can simulate 1 point and use these surrogates to map and get the results from 5 points. So kind of a 5-to-1 ratio in terms of savings.
This podcast is sponsored by Siemens Digital Industry Software. Learn more about their simulation and test solutions by clicking the links in the description. Build a better tomorrow faster with SimCenter. Welcome to a new episode of the Engineered Mind podcast. I'm your host Yusuf, and on this podcast I'm talking to researchers, scientists and engineers and how their work is shaping the world around us. For this episode, I'm very delighted to welcome an AI expert, namely Justin Hodges, to my show. Justin is a senior AI ML specialist and product manager at Siemens DISW. He has a bachelor's, master's and Ph.D. in mechanical engineering, specializing in thermofluids. In this very exciting podcast, we talk about myths in AI for engineering, how AI rather augments engineering workflows than to disrupt them. We talk about how tools can bridge the skill gap of engineers who are not data scientists but want to use the algorithm and techniques to leverage their test and simulation data. Justin and I cover the interesting aspects of physics-based versus data-driven approaches. Justin will walk through some use cases in the industry, how you can get started in the AI space as an engineer, and so much more. If you would like to support the podcast, make sure you give this podcast a like and leave a comment down below to make sure the ominous algorithm is suggesting the video to more inquisitive scientists around the world. Subscribe if you haven't already. And now, ladies and gentlemen, enjoy my podcast with Justin Hodges. Ready to roll. Justin, thank you so much for doing this. Welcome to my show.
Hi, thanks. Always nice to talk to you.
Very cool. We've been in touch for a long time, Justin, mostly via LinkedIn. Today we will talk about artificial intelligence and simulation, but maybe not primarily simulation, also how AI can augment testing scenarios for engineers and R&D processes. Can you give us a little bit of a background? Who is Justin? What do you actually work on?
Yeah, definitely. And I think what you just touched on as far as simulation and test and machine learning is in some order my background. So I did my bachelor's, master's, and Ph.D. at the University of Central Florida, mostly in turbomachinery, aerodynamics, and heat transfer, traditional mechanical aero hybrid track. Fell in love, I think, with this sort of field when I started taking boundary layer measurements on a wind tunnel, so I can appreciate the test side. And then, somewhere throughout and into the beginning of my PhD, I took an internship with our health engineers group in Princeton to apply AI and simulation to healthcare problems, specifically this thing we patented for diagnosing COPD. And then I realized, wow, like all the interns I hang out with and drink coffee with, like their day job is replacing traditional simulation bits with AI. So I realized there was a lot of opportunity to leverage what was being cultivated into our traditional, fluids and thermal simulation and testing sort of track. And since then, which was in 2017, I've been on a very consistent vector to just absorb and build up as much AI expertise as possible. And my current role is AI and ML technical specialist in our Siemens business unit, which focuses on simulation and test software.
Really interesting. Cool. Thank you so much for the introduction. Now let's maybe to set the stage, let's talk a little bit about AI for CFD maybe at the beginning, because I know I'm a little bit in the Twitter space and there's a lot of pushback, especially for the from the classical mechanical engineers saying, well, AI is just statistics. We don't need it. We don't use it. It will never replace simulation. Maybe let's start with some misconceptions or myths about AI for engineering R&D or in general, some myths that you would like to clarify.
Yeah, sure. So you can certainly augment someone who's using the software to be better and more productive and proficient, but you cannot replace them. The knowledge they have on the intimate technical details on the application of what they're actually trying to solve, so like traditional knowledge of fluid mechanics and that sort of thing, as well as the understanding of the numerics and whatever they're doing, that's pretty essential to have in terms of a cookbook recipe of that plus whatever machine learning approach. So it's not like a unilateral replacement for sure. But there's been various symposiums by, you could say, like the classical people in terms of physics and fluids and stuff, and they've addressed that it's machine learning, data-driven techniques, etc., are really helpful to supplement in certain areas, but again, not to replace. So that's one. I think that's the big one. AI can't be used for everything. So there are certain cases where it's an absolutely killer application of machine learning to like a given task or given simulation or design project. And there are others where it's like really forcing it in. The analogy I use is lighting a cigarette with a blowtorch. Just why, you know? So yeah, there's also a choice of where to use it. And there's some really killer applications, but as well, there's some that are unnecessary, and there's some that just don't fit the method. You know, it's not an appropriate method for that. So yeah, those are a few to start out with. I bet you've run across a few yourself, though.
Yeah, I like that you mentioned the substituting part, because I think AI is actually here to augment engineers or engineering workflows in general, not actually here to replace simulation. I feel that one of like a little bit of pushback is also coming from engineers because they might be afraid their job might be taken away, whether that's in the simulation or testing space. But what we actually see, and probably you as well, is that in the industry, it augments your workflow. So AI plus the engineering expertise is actually the best combination of both worlds. Would you disagree?
Yeah.
Or would you agree?
Yeah, I definitely agree. And you can look at the rate of progress too, to sort of evaluate a claim, like how unilateral takeover would happen in terms of like a given approach. And then one day it would just be purely machine learning, whereas in the past it was purely like some numerical approach that's traditional. So I would say 2015, 2016, these core AI and ML organizations, industry teams, universities, those core groups doing the innovation and research on the methods themselves really started producing these technological advancements, inventing the models and algorithms. And it's subjective, but I would say around 2019 and 2020, it really became clear in some of like the Kaggle reports for what's going on in the landscape and advancements in data science, machine learning, where there's a lot of focus in literature and code distributions on application-oriented innovation. So like taking what's been made and then proliferating it into applications like, our community of engineering simulation. So, okay, well, in 5 years, how much has happened, right? There's been definite use cases that have been really successful. There's been some improvements in areas, and there's been some big wins, but there's not a paradigm shift away. Like people are still using simulation as they were 5 years ago, right? So, it's very supplemental. It's very useful, but I don't think it will replace people in terms of the traditional approaches anytime soon whatsoever.
Definitely. When we talk about community, a word that you just mentioned, I think we should also talk about the so-called democratization of AI. Usually we talk about democratization of simulation and cloud-based simulation and whatnot. But how do you see the democratization of AI also when we think about the skill gap challenge? Because a lot of people, or engineers in general, we are very inquisitive people. We love doing simulations. We love building models, building simulations. But how can we bridge the gap between I'm not a data scientist myself. I'm an engineer. I have the expertise, the field expertise, but I want to use AI. So how do I bridge the gap between this delta between I want to become a data scientist, but I'm actually an engineer? How do we bridge that gap?
Yeah, that's a complex answer, but it's a fun question because it's kind of the natural progress of things. There's always new tools being introduced into the engineering world and industry. So, for fun, next time you talk to someone who did their Ph.D. in aerospace or mechanical, ask them how many systems engineering classes they've taken or, core programming language classes they've taken. It's probably going to be a small number, even if they're extremely renowned in what they do. So, you could say it's a similar sort of progression that's happened with us using all these numerical approaches in terms of like the core bit of what we do for our job. And, obviously they take commercial software, people take commercial software and make adaptations and custom codes and open source bits. So it's a familiar challenge, implementing new things from our core disciplines and foundations and what we've learned. But I think a big thing is on the software providers commercially to make it so that non-experts can use it. Because I think a core requirement is that if someone's designing, a medical device with CFD or whatever it may be, that they can focus on the tenets in their design and their problem, and not the core fundamentals of how a neural network works. And I think there'll have to be some leaders in the organizations that advance the methods development in terms of like what their teams use to design their components and stuff. And they'll have to be more technical and become a bit of an expert in machine learning. But the tool providers have the major burden to make this wide democratization available. And, you see plenty of examples out there already, Monolith AI being one of them, right? My wife's not an engineer or in science in terms of her career. And one day I think she did a tutorial by herself, really. I don't know if she knew what she was doing, but, that was the point, is so easy to use. She's pretty smart, but, I think that's still a pretty good milestone, little test in terms of how much of a non-expert you can be and use the tool. So, there's that, and the aim should be a persona of a large audience that does not know about AI and ML. And again, like there are parallels. You can compare it to optimization, right? How many people know the core steps inside the algorithms for optimization or of their sampling that they're doing? Not so many, probably, 'cause that's not their job. But it's similar. They learn how to use it, limitations, things like that. They have easy workflows from commercial providers. But yeah, it's certainly an interesting thing and unique because it's kind of a pipeline, like in Monolith AI's product. It's really like a pipeline. So you're not just taking data, pressing a button, and getting a result. You do have stages to analyze it, manipulate it, filter some data points out, do mini experiments. So sure, it's fair to say there's maybe an extra step or two in terms of the non-experts hoops that they're going through in their process.
Yeah, interesting. How do you personally approach this? So your AI journey, I'm not sure how long have you been doing this now? 6, 7 years maybe? Like the AI path? Roughly 6, 7 years?
Yeah, the first professional experience was in 2017. So
Okay.
a few years now. And oh gosh, such a large journey. So if I say like, well, what's happened since then? For sure, the first one was fundamentals. And that would be just like very simple books on concepts, very simple classes. I really like the Coursera one that I think everyone's taken. That was a really good one at balancing the fundamentals, the concepts, and the applications. But I think sometimes it's easy to get into a routine of just like reading too much, whereas you may not feel confident to, but probably should just start jumping into specific, coding examples and making things from scratch. And I think that helps build a lot of confidence. And then to all of our attendees who listen to this and do CFD and simulation and stuff like that, I think a big problem is there's not a ton of open source data sets in our community, right? Not maybe ones that are suitable for machine learning. So, if you don't care about engineering simulation and you want to do, image recognition or something, there's a ton of data sets you can just one line of code and download into your notebook, but it's not that easy for machine learning in like CFD or finite element and stuff. So that's one kind of key thing I would do, read, learn the fundamentals, practice on non-engineering simulation type examples, and then be intentional, try and gather some data and then have a thought of a hypothesis or something you could test and just see what happens, because you'll go through the steps and headaches and you'll learn, I should remove these data points. That'll help. I could do this transform. It works, but only on these cases. Optimization of the settings you use and hyperparameters and that sort of thing. So I think that'd be a pretty good flow. After that, you'd feel comfortable to branch out.
Very cool. Yeah, I would also be interested in we talk about data, which is the lifeblood of these AI algorithms. So the question would be simulation versus test. And before we jump into onto the hype train of, or like the topic of data-driven versus physics-driven approaches, maybe talk about data in general, and then simulation and test versus test. Where do you see the bigger ROI and why? What are the pros and cons when we talk about AI plus sim versus AI plus test?
Yeah, that's a good question. Hard to generalize, but I think I can definitely lay down some guides. So I would say there's an implicit benefit available in doing AI plus test.
Mm-hmm.
Because you think about like anyone that does simulation already is sitting on a pretty large ROI to if they had built the experimental rig themselves, done the testing, acquired the data, made their empirical correlations, and then finished, rather than avoiding all of that and doing the simulation. So, you could always say, well, if I had to do the alternative and pick between either simulation or test, it'll always be much bigger time savings to avoid building a test rig. And I remember the day that I think I broke like a sensor in the wall of our wind tunnel. And I was like, I'm not building test rigs anymore. This is like 3 months to build the rig and then a month to do the data acquisition for that project. But anyway, yeah, I'd say generally the test and plus AI use case could be marginally to significantly higher ROI, depending on the project or the work that's being done. Um, yeah, I mean, we could really go to the next step and talk about a lot of different things. What do you have in mind?
Yeah, I was also thinking, in simulation wise, what do you think are one of the problems? Maybe let's not call it problems, but intricacies when we talk about simulation. Maybe it's that it's based on very complex assumptions when I build a simulation in the first place. So I'm an engineer, I'm sitting in front of the computer. I'm biased as an engineer. I'm building the models. Maybe the mesh is wrong. Maybe the numerics are wrong. What else could be wrong? Like where you see the big benefits compared to test. If that question makes sense to you.
Yeah, just generally, what are you capitalizing on when you're using AI in simulation? That's unique to simulation, I think. So, it is inevitable that people will use software in what they do. So it is a requirement to release these augmentations to simulation. And I think a lot of that is the same thing you experience when you use your iPhone or any other non-engineering product. I mean, it has to be intuitive, usable. It would be great if we could start controlling our software in our engineering work with voice commands and stuff like that, like, any other device out there. So stuff like that's inevitable. And that falls into like a workflow and usability use case. I think it's safe to say engineering simulation is getting way more complex over time. First I'll do just aero, then I'll do aero and thermal and model the solid pieces. Then I'll throw in the actual stresses and include those. Maybe I'll do some acoustic stuff as well. So then we have this very transient case with all these physics. So naturally, setting up these files and analyzing them is taking way longer. And it would be great to have like workflow assistance, automation, forecasting, because you could save out on a missed run that's flawed or doesn't converge. That would save you a bunch of time to not set up the model, those sorts of things. So I would say specific to simulation, there's this workflow aspect, assistant, however you want to describe it. And especially at Siemens, we have a huge portfolio of products, and they're envisioned to be used together by the customer. Not all of them, but not just one of them. And so you really have a great opportunity to synthesize what happens when you run a few of those tools together, and you have something that can overlay, like Teamcenter or TC-SIM, with some implicit machine learning technology to pull semantically information from different simulations, make meaningful conclusions, make a model to give it to you. So yeah, I think these are some valuable use cases for simulation that stand out, irrespective of test. Different things, cherry pick.
Maybe if you talk about a simulation use case, maybe in the turbo machinery space, does anything come to mind? For example, turbo machinery, maybe walk through one use case just then, and maybe from the start to the end. Like how did you collect the data? How did you feed it into the AI algorithm, the ominous AI algorithm, and how did you draw conclusions? And how did it actually affect like the engineer's work, or what was the ROI?
Yeah, I think it's a good point. I think the audience would like to hear that. So I'll pick something actually we did collaboratively with Monolith to sort of anonymize, what it was, but make it still very clear, like the steps and the value and stuff. It's very common for an equipment manufacturer or a company that's producing equipment or designs and fabricating them. They'll do a bunch of different tools along the way in their design process that increase in fidelity. And essentially, you might start out by something that's really giving you rough estimates of results, covering a vast space. The engineer makes a few decisions on like which ones to focus on, like which parameters are really sensitive to the results, which parameters are we going to lock in and not consider as variable in future, and then progressively like feed those results to another tool, feed those results to another tool, and then eventually you go from one component to maybe like a full, stage or system of components, really. So you're broadening in terms of like what you're simulating to be more of the whole thing, whole picture, whole assembly, etc. And then also, increasing fidelity. So initially it could be a simple arrow, etc. So one thing we did was we basically said, let's speed this whole pipeline up. Someone has to do 4 tools, start to finish, in their design process before they submit their final design. What if we could just interject AI after, say, step 1? And what it would do is you do the first simulation that you normally would do. You get the results you normally would. Nothing's changed. And you take those fields of scalars, say temperature field, whatever it may be, and in your pocket, you know the variables that are for the geometry and the operating conditions that are associated to those designs. But what if you could use those as inputs to machine learning model, and what it would predict would be the results of, say, step 2 or step 3. So now you have more expensive simulations in product number 2 and product number 3, and you can just sidestep them, right? You can jump kind of to the end of the process where you're maybe doing one more simulation and your inputs are not like the results from step 2 and 3, but this AI model that's intelligently mapping from the earlier days. So ROI-wise, this is huge because I think obviously everyone cares about accuracy, but throughput, meeting deadlines, exploring this vast space that exists now as we have all kinds of opportunities and solutions emerging, right? Electrification and all these different options now that like a turbo machinery company, aerospace, or automotive company could have. So that's a huge ROI. They could save 50% of their time or something like that. So you're realizing like a lot of this is a supervised learning scenario. So implicitly, the starting point is, they have past project data from the different steps in the software, step 1, 2, 3, 4. You train these models and do numerical experiments to take output of step 1 to predict, the results that go into step 4 for the 4th simulation tool. And you do these experiments to see how general they are. So, if I train on 20% of the data available, and I choose it in a wise way, like in a space-filling way, how vast and diverse of cases is it accurate on at the latter stage in the final product, right? And you make these sort of bases on what you need to train on and what data you thus need to provide. And essentially in that case, it was something like if we ran 25% of the simulations that we normally would have without machine learning, it could repopulate accurately the entire space of the simulations that were the basically results, like the end results. So I hope that's not too vague, trying to be a little bit anonymizing in terms of the scenario, but I think that's a prime example on ROI and faster throughput. It's basically surrogate based. People call it reduced order models, response surfaces. We can consider this like an advanced version of that. Monolith is great at introducing machine learning models and algorithms that can capture 3D spatial information, which is quite rare. So you see a lot of tabular-based focuses in machine learning in different industries, and computer vision, which is highly 2D image-based and stuff like that. So yeah, it's making these advanced surrogates and ROMs, and it's essentially allowing people to use them in place of simulation. And they're not doing simulation, but they're getting to their results, much faster and then spending that time, say, optimizing the sweet spot in their design space to get a much better design. Or, in that case as well, it's not just about finding the best design. You have to also make sure that if you say you're designing a rotating component in a turbine engine in an aircraft, well, that thing is running for a variety of circumstances and variety of operating conditions. So even if it's the best design at the nominal conditions, baseload, etc., it needs to perform well and not break and not violate the criteria that it has and the constraints on where it needs to operate for all of those other spaces, all those other design points. And that could be thousands of points. So no one wants to simulate thousands of extra just to be safe, right? Let's make some surrogates. And then maybe in other use cases we've seen, you can get basically a 5-to-1 ratio when you explore this sort of CAD sensitivity, reliability, and robustness space. You can simulate 1 point and use these surrogates to map and get the results from 5 points. So kind of a 5-to-1 ratio in terms of savings.
Mm-hmm. Yeah, that makes a lot of sense. You've touched on a lot of points. For example, when we talk about DOE, so design of experiments, I think what the big advantage of AI is, first of all, when we talk about complexity, so let's say if you have something like, 5 or maybe even 7 input variables, when you do a DOE, it would probably be like, 128 experiments, where in AI, you could basically narrow down the number of experiments or simulations you want to run. So it gives the engineers kind of a path. It guides them in a certain direction, saying maybe run this simulation or run this test. So it is way more precise than actually doing or thinking about DOEs in terms of let's just run 128 simulations. Maybe you don't have the capacity or the time to run these simulations. But then also on the data aspect, Justin, when we talk about data, usually when we think of we have a lot of data available, or as you've mentioned, there's not the MNIST data set in terms of engineering data sets. What if we don't have enough data? When we talk about data augmentation, synthetic data, what can we do as engineers to maybe augment our database?
Yeah, that's an ongoing consideration for us because every simulation, or even more so, test point costs money. Mm-hmm. So how can we deal with, from a machine learning point of view, very low amounts of data? And you can do things like removing outliers from your data. So counterintuitively, removing data would make models more accurate and more robust. You can do things, like you said, to manufacture fake or synthetic data. There are methods like lasso or things like that to just synthetically resample a given data set and then retest for that subsample what the general result would be. You can do transformations as well. That's not just specific to small data sets, though. You can imagine a movie rating system, 1, 2, 3, 4, 5 stars for a movie. I mean, how many of those are going to have 4 or 5 stars, right? Or 1 star? Probably a lot more than 2 or 3. So maybe that's not the best example, but I think you can get the picture that you can have some of these cases where the same results keep showing up, and you can do logarithmic transforms or things like that. Or in our problem space, you could consider some sort of encoding systems, because maybe you have 100 options or something crazy in terms of your independent variables, or your inputs to machine learning. But your data is really sparse. So maybe in each run you have 10 or so populated and the rest are 0 or invalid or null or whatever, empty, essentially. Yeah. So you can employ encodings and that sort of thing to try and help. I like the parameter space thing that you touched on, and that's also a relevant play for analysis or for a case where you don't have enough data, because and in some aspects it's about a ratio or an aspect ratio of your data set. Maybe 100 cases is enough if you have 4 independent variables. But if you have 20, then different story. So in some cases, you may have a couple hundred simulations or whatnot, but you have far too many variables. And one thing I really like that Monolith has is an autoencoder, where you can essentially create a latent space. It's almost the familiar example for the non-AI enthusiast is principal component analysis, or Ph.D. or DMD, or whatever you want to pick from, where essentially you capture the primary modes or influences in terms of the variables on the result, and you basically distill down to just focus on those. So now maybe instead of 100 modes or inputs, you just consider like 20. And then the representation on the result may be like 95% or something with just the first 20 modes. So the distinction is machine learning can do this, but also consider highly nonlinear relationships, unlike other approaches that I've mentioned. So that can be a really, really effective way that's very common in these sort of studies where, sure, I have a marine ship design, but there are 25 variables and I have 200 simulations. Well, what happens if I could reduce that input space to, say, 10? Right, that's much better. And that is kind of a small data problem or solution. So yeah, I think that thing you touched on there in terms of re-representing the parameter space in a latent dimension is great.
Yeah. Usually when we talk about the latent space, usually denoted by Z, it's always that you have it in form of numbers, but then we talk about interpretability. I think it's not only critical for medical aspects or medical applications, but also for engineering applications. Let's say, I don't know, maybe you have a use case in mind, Justin, where we talk about turbo machinery applications, and it's very safety critical. So how do you verify and validate AI algorithms? And also, how do you make them more interpretable so an engineer could see, okay, the algorithm made a specific decision, and this is why, and so on and so forth.
Yeah,
maybe intervene in case the results don't make any sense at all.
Sure. So turbo machinery example. Let's pick one. So really famous sort of thing there in terms of canonical cases is like a jet and crossflow problem. A lot of people do that to validate cooling strategies for turbo machinery. So an example is, the application really is you have all these hot components. They're operating in an environment, 1,000 degrees hotter than their melting point. How on earth does that happen? Well, they have really elegant cooling schemes. And a big component of that is, little tiny coolant jets emanating through these metal surfaces to provide protective barriers from that heat flux in the mainstream. So, as you can imagine, there's a lot of groups validating different CFD models, different designs, numerically in CFD for a simple jet and crossflow problem, several jets and crossflow. So if you really hone in on that example and say, well, what's the way to make that interpretable and trust a machine learning model? Because, by the way, this is a very common pairing, turbulence modeling and machine learning, things like that. So, first is choice of models. Some models like neural networks or the autoencoder approach are highly opaque black boxes. You can do trickery to sort of learn, sensitivities between the things you put in and the things that come out, but it's more advanced and implied, I would say, than sort of obvious things like if you choose a random forest, you can directly expose and call on in a lot of Python libraries for random forests, what's my feature importance? And if I'm looking at the jet and crossflow problem, I may have inputs like the diameter of the hole or the ratio of the speed of one stream of air to the jet air, right? So if I'm trying to learn, hey, just predict the temperature field, I can learn the sensitivities on which ones feature-wise are the most influential and the most important on that final result. So things like that you can make interpretable, or you could allow interpretability if you formulate that and just simply choose those models, right? People also go for linear models as much as some people hate to hear it, polynomial models. Those are more interpretable than neural networks. Also, there's ways to get uncertainty from a lot of models. So that also helps. Basically, it's telling you, I'm this certain in the prediction here, maybe in this part of the domain, or in this part of the domain, I'm completely 50-50 almost, right? There's a huge amount of uncertainty. You can take interpretability out of that. But I would say, I really love the example of the different domains of the boundary layer and a turbulent boundary layer. As an example to say, how can you make your problem interpretable? Well, what if you choose things with engineering knowledge as your inputs and not just arbitrary combinations of every variable possible? So in that case, like we know the boundary layer regimes are highly segregated by Reynolds number and wall distance and fluid properties, velocity, etc. So what if we just simply choose those as our inputs to our study in that case, rather than say 20 state variables, just throw everything at it, right? So I think going into it, choosing the right models, um, using some basic analysis on uncertainty and areas where it's doing well versus areas where it's doing poorly, and then also the way that you cast your problem. If you want to cast it in simple terms with like things like Reynolds number that you can relate to and understand, then that certainly helps more than like just say derivative of tensors and properties of temperature, pressure, velocity, UV, X, Y, etc. It'll probably mean more to you if you cast it in those parameters that are familiar and used for correlations themselves.
Yeah, I think rather than modeling, maybe to take a step back, and because we talked in the beginning about data-driven versus physics-based simulations, it's maybe also when we think about not explicitly modeling the physics or like writing equations, but rather maybe having the physics inherently in the data, such as test data, and kind of extracting it, quote unquote, from the test data that you've collected and kind of learning from that physics without actually learning the physics, if that makes sense.
Yeah. I think so. That's a good point. And to put a backdrop on everything I've been saying, to your point, if I'm simulating something and there's some error that's associated with the simulation, if I just look at the results and I train models to predict those results, then I'm also including the error in the simulation in terms of what it's predicting. So that will carry through to your point, right? I'm not, minimizing error or residual or however I'm going to quantify error. I'm not trying to minimize that by learning equations and including those formulations, etc., for the PDEs. I'm just simply taking the result at face value and saying this is the answer, and that's not a perfect assumption. But you're right that that goes away when you do physical test data. If I have some sensor and I measure time series, yeah, I'll have bias error in the instrument. I'll have precision-based or user-based error in terms of systematic ways of taking the data, right?
Yep.
But it's different to say than all the sources I just mentioned on simulation.
Very, very interesting. Generally, when we talk about error-based approaches, we talked about safety-critical applications, and we talked about the error. So usually when someone gets started as an engineer, learning about machine learning, they talk about accuracy and whatnot. And if a model has 99.999% accuracy, it's probably very good, so I could deploy it into my real-world application or with my real-world application. What do you say to this? Like, what metrics would you personally use to determine if an algorithm is good enough for engineering applications?
I think I understand, but let me reiterate just to make sure. So if I'm doing simulation to predict a result, and I use machine learning instead of that simulation, then you are saying what metrics would I use to have confidence in the machine learning model versus a simulation? Or do you mean something different?
No, exactly what I said. Not only simulation, but also testing. For example, let's talk about, I don't know, AI plus test or AI plus sim. Would I only use accuracy, or would I use any other metrics that I need to have a look on before I deploy my model into the real world?
Yeah, I think a big thing to consider is just how general it is. You have a certain number of parameters that are inputs, essentially knobs that you're turning around and training the model to accurately reproduce the outputs for those scenarios. So a simple thing to do is to simply use the model that you've trained on cases outside of the bands of what you just trained on, which, to be fair, is a pretty easy thing to do because if you have 1, 2, or 3 dimensions, it's pretty easy to keep track on the ranges for everything you've trained on. But if you have 10 or 20 dimensions, it's hard for us humans to, understand conceptually, or at least think about where we are interior to that space. So I would say that's a key consideration, is looking at where you're providing inference in terms of your independent variables versus where they were trained. Or you could just do simple things like if you have a high amount of error, where are you compared to the mean of all the values you trained on? So maybe for some of the or several of the independent variables, you're kind of at the extreme, like the max ranges of what it was trained on. And if you do that for several cases, if you have that situation where you're pretty much at the extreme min or max of some of your input variables, then yeah, you're training on kind of the fringe of the space of you're providing inference, on kind of the fringe of where you trained. So you can expect that you may have a lot more error than when you're at sort of the center of the cluster and where you trained. I don't know if that makes sense, but that's one thing. And then also, you could do k-fold validation and other more rigorous ways of validating. So, in general, just don't in one shot do all of your training and then all of your testing and validation, and then say, this is it. This is my accuracy. Take different subsets, repeat that exercise, look at the error in each of the subsets, and then see how different they are. See how much different each of the errors are. And then for that matter, I think at least some of the times, there's still this distinction between training, testing, and validation. And I would say, you should carve out data aside that's not included in any of the process for validation, so that when everything is said and done, you test on those cases. And I would say choose those intuitively with knowledge of your problem. So, a relatable thing to turbo machinery would be, if this is like a compressor application or something, don't set aside these cases for validation at the mean RPM of your full test data set. Pick some intuitively scattered throughout the range, and then notice if you have higher errors at low or mid or high values in the range.
Yeah, that makes sense. Yeah, got it. If the audience has any more questions, they can put their comments down in the comment section and let Justin know if they have any more questions. Regarding maybe a first project as an engineer, if they want to delve into the world of AI and sim or AI plus test, would you recommend them any startup projects what they could work on? Whether that's a simple, 2D CNN used on simulation data to reproduce some results, or train a CNN on simulation data.
Yeah, that's certainly a good one. Yeah, that's a good one. There's a few. So I would say there's certain academic groups that provide validation, especially experimental validation. So I think if I say it out loud, the acronym is ERCOFTAC is one.
Yeah.
That's a very famous one for providing extremely robust physical measurements of simple canonical cases like, flow over a backwards facing step, flow over a cylinder, or, converging or diverging nozzle, that sort of thing. So maybe those correlations in data is publicly available. And then right there you have, some real physical test measurements that you can do. But more accessible is probably some of these codes and things like that you see that are 2D in nature. So like you said, flow over a cylinder, things like that. You could probably access that data or the tools and regenerate the data if you don't have a tool already in your belt to use to generate data. And then I don't know how easy this data is available, but tabular data is pretty huge. I don't know if it gets all the appreciation it deserves due to lack of eye candy compared to spatial stuff and whatnot. But yeah, I think that's one of the most common things. So any scenario where you have a bunch of runs summarized into 0D metrics, and basically you could use tree-based methods or a variety of other methods just to tinker and learn and play in a sandbox on tabular data to see how well you can capture trends in a tabular setting. But in terms of the other stuff I mentioned, you've mentioned the 2D airfoil, that's a really good one. I think there's workshops and databases and conferences that have challenges or workshops or whatever it may be called, like the high lift workshop, where they take a very high lift airfoil case and basically participants in the session would simulate and predict drag and things like that. And there'd be a comparison round on who got the most accurate and kind of all the methods people tried. I think that data is usually made publicly available, so you can try out these conferences that provide data, and then kind of just have your hand at it in Python or whatever you want to do. And you mentioned CNNs. I think those are great. Certainly applicable outside of engineering simulation. So couldn't hurt to do that. And those are really elegant too, in terms of once you want more complicated data, those play really well at working because some of these don't work.
Yes,
I would say a really cool thing to insert in this convo about things to try is Google Collaboratory. I can't
Hmm.
speak highly enough about that experience. I could drop a link in this chat, and within 30 seconds, you could be running my code. You don't have to install anything. You don't have to have a GPU. And furthermore, if you wanted to get serious about the projects you're running, you can get access to very expensive GPUs and hardware for like $10 a month. And that's basically like hundreds of gigabytes of storage, access to all these crazy GPUs, and basically pretty high leeway in terms of how you run the job. So they can run for a while, you can leave and come back, and it won't disconnect your session. I mean, it's pretty amazing. I'm excited for our engineering simulation world to reach that level of maturity where anyone can just log in and within 30 seconds be running code. You don't have to worry about dependencies and all this stuff and libraries. It's just, I would do a lot of sandbox playing around in there for sure.
Really cool. Yeah. Really cool insights, Justin. Thank you so much. Also, we've talked about before the podcast about CFD and NFTs. If we combine that, maybe in the future. So, if we talk about the future, where do you see the future of AI in the engineering space is going? Will we have CFD NFTs in the future? Maybe not. Where do you see the future going?
Well, if we have another lockdown, then maybe you and I will make a CFD NFT and then we can say they were done just because that would be cool. Um,
Definitely.
but I think in terms of the future, I don't know, it's hard to say because I would just think of the normal things that aren't necessarily what you'd think of with AI, right?
Hmm.
Like metaverse, cloud based usage. These are really big trends. And I think that AI will play to its strengths in such implementations, right? If you talk about a metaverse, it makes perfect sense. There'd be AI surrogates in there that could give you real time results, right? It's a bit harder to imagine a metaverse where, okay, I submitted my simulation. Let me come back in 24 hours and see what it did, right? That just doesn't fit the mentality or the stereotype as well. So
Mm.
I think a lot of these things are cooked in. I think there'll be a lot of things behind the scenes that are AI powered features. Like we mentioned, voice control over simulations and stuff. I mean, right? Like a lot of these things, maybe there's solvers were placed in the back end. Some of it may not be obvious for that reason. Some of it may be just cooked into or what everyone in layman's terms is thinking the future is going. And then some of it I think will be pretty in your face as far as like, wow, look what AI can do. And I think we're seeing examples of that in academia that are really exciting. So it's a broad net, but that's some things I think about. What about you?
Good question. Maybe I'm not sure if the audience knows it. DallE from OpenAI, like basically you give it a text and then there's some natural language processing and transforms it into art. I was thinking maybe in the future if you have like kind of a software for engineers, you type in I don't know weight optimized, I don't know whatever shaft, with these and these constraints and boundary conditions, it would just give you the shaft like in a couple of seconds. That would be pretty cool. It might be even I don't know maybe in 5 to 10 years that this is possible, considering that yeah, even stronger GPUs will come out and algorithms. That would
Yeah,
be really
I
cool.
think I think the envelope of feasibility, it is certainly inside that, right? It's almost like if you look at really advanced like military technology or something, I mean, usually stuff is there possible way before it's just commercialized and distributed to everybody. And mostly I mean, I don't want to generalize to that scenario I'm not familiar with, but back in the world of commercial software, um, I think about there are a lot of things like ASAP customers are asking for
Hmm.
really big capabilities that will make a difference without any doubt, right? And then stuff like that is like in this conveyor belt that's coming and is waiting for other things to kind of get cleared out that, has been in queue already and has like no question as to the value that it will add to customer designing, like back to like a medical device or something, right? So, yeah, I think it's not far out of reach in terms of the technology being able to do it today. And again, it's more about just taking time to go through roadmaps and become products, and then it would be there. But yeah, I thought about that too. Like, what if I could just be doing things and be on my way, and then just bark out, please run this simulation with this boundary condition, and then I
Hmm.
could just check back later, like what the result is. That'd be so much faster than okay, let me open terminal, kick off a job, whatever.
Yeah,
But
definitely. It's gonna be very exciting, definitely. Um, Also, a question I would have, probably also interests the audience, is if AI is so cool, so fancy, why is not everybody using it? Like, how do I pick a business case? How do I decide if something is actually a AI worthy case in my business?
hmm,
How do I decide it? We talked about data. Data is one point for sure. Maybe what's the business outcome? Anything else that you could think of?
certainly a nest of things. But I would say, kind of back to the jokey type stuff we talked about as far as how many mechanical engineers take systems engineering classes in
Hmm.
university.
Yeah.
You can make the same joke for machine learning based stuff. Probably a few right now. So I think that it is an asset to have. It's a commodity, not just to have data, but to have data science and machine learning competencies in an organization.
Hmm.
And when you don't have enough of that, um, things scale a lot worse. And I think scale is a primary consideration for someone starting a business. So, for example, if I make a piece of software, I can distribute it widely, have a nice margin on it because it scales very, very well. I can sell more of it, etc. It's not that simple, but you get the gist. Now, if I have to teach everyone at every company a set of things before they can use it, and it becomes a very services based situation, then the scaling is harder because the more people I want to onboard, the more people I have to do the onboarding and to teach them. And so I would say that once more and more people have at least some competency and literacy in
Hmm.
data science and machine learning, then that problem will go away uh, at least a moderate amount. And you'll notice probably a difference in uptake and things like that. Um, and I think it does go back to, like you said, data, right? This is an essential piece.
Hmm. Also, when we talk about data, some companies might not even know that they could use their historic data that's laying around somewhere. Maybe if they're very lucky, they have a data lake somewhere, and some of them are not even leveraging that data. So it lays around somewhere, and they'll be like, okay, it's probably garbage. I'm not going to use it. But maybe they have some 3D data, tabular data, some CSV format files laying around that they could apply AI algorithms on and actually extract knowledge from engineers that have been retiring from the company and make use of that for the future generation of engineers. So yeah, any other pain points, Justin, that you could think of in terms of like maybe your day-to-day work, engineers, what they are struggling with when they get in touch with AI for the first time? Do I even trust AI? Why would I trust AI in the first place? But also maybe onboarding AI, how do I integrate? Because AI is a disruptive technology. How do I integrate it into my workflow and engineering R&D process? But then also, how do my engineers use AI? So there's a lot of problems that engineers have to think about, maybe in the C-suite. Why would I use AI? I don't want to lose track or like the. I also want to jump on the AI hype train, but maybe don't want to jeopardize time to market or be faster than my competitors. Like, what
Yeah,
do you say?
sure. I can start firing off some pain points, considerations, etc. So,
Mm.
one would be connectedness in terms of all the different tools involved. If we're going to take data in from multiple sources and consume it into a machine learning model, we want to use the model later for inquiry and predictions, and those probably will be routed to another tool. A lot of people take our commercial software and others, and they make highly specific systems for running it and providing input to it so that they can just execute the processes faster, maybe without even opening a GUI, just doing all of it from terminal. So people already spend a lot of time on the connectedness between the different software and how the user would interact with it, and maybe like text file based usage and output and stuff like that. So just simply put, not AI specific, but if I introduce a new tool, then it has to spend time to go into that process to be used in their workflows, and their users need to be educated, and surely there'll be issues. So then they need to make documentation and best practices to use it, etc. So not just connecting the models to their sources, but also just generally speaking, an uptake in people doing their day to day work, and then feeling bold and brave to do it a new way and maybe get issues on an IT side. So that's one. Trustworthiness is another. Um, if I have a CFD simulation that crashes or a physical measurement that starts to become clearly an anomaly or like bad data, I have tools to diagnose what's going on and I can fix it. But many people may not feel the same way if they're machine learning models, and maybe the results are bad and they know it, they don't know how to fix it, or B, they don't know the results are bad. So there need to be guide rails sort of put in by the experts to make that really foolproof for everyone that's using it in day to day. Other challenges, yeah, I mean, there's a lot, so kind of depends on the problem. But
Yeah, definitely. I think you covered it. You covered it quite well. So these are probably the main pain points, and then, as you said, case dependent. There would probably be more problems, such as integration, other tools that I've been using, traditional R&D tools. And then how do they integrate into the whole workflow of? I'm doing my simulation. I have a CAD designer maybe who's doing like collaborative work with a simulation engineer. And how do I integrate that AI tool and kind of like still augment both, but not replace one? Maybe that's a tricky one.
you had a good example earlier
Yeah.
too. You said that a lot of companies would have data and they have to go through and basically prepare it in a way that can be used for supervised learning exercises. And that's the pain point, is that takes time, and those people are probably busy to do other tasks, and they see it as, rightfully so, that maybe they can't do those other tasks because they have to do this one. So they have to kind of wait until they're in a season where there's no urgent need and they can afford to take 20% of their time to annotate data and prepare it and analyze it and then decide, again, if they have machine learning expertise, to know which data is the right data, what the limitations are, which cases to use, which ones not to use, etc. I mean, that's not a trivial decision. So a pain point is, finding the time and personnel, really. That's a huge one, actually.
That's That's true. And also regarding the data, where's the data laying around? Who's taking care of the data? Who has the data sovereignty? I think is the word. All these kind of questions that have to be answered. So yeah, really, really tricky. But let's see what maybe in the future there will be more guidelines on how to deal with this kind of problems. But yeah, any closing remarks from your side, Justin? We're hitting the 1 hour mark. Had a few problems recording today. Not the luckiest day in terms of doing a podcast. But any closing remarks from your side? Anything you want to tell the audience? If they want to jump on the AI hype train, if you want to call it that way.
Just be persistent and don't give in to maybe self-doubt or imposter syndrome. Engineers learn incredibly complex things in school and are good at accomplishing and learning new things. So just don't give up. And I'd say networking is very important. There's a lot of problems to solve with machine learning in our applications. So follow the right people, read their papers. I think reading literature is one of the greatest things you can do. In my mind, in grad school, I always thought of it as, I don't know all of the words or concepts in a certain area until I am taught them to a degree. I mean, that's pretty literal, but kind of thought like I am only going to be as good as the papers I read for a long time until I have a really nice base. So, I would say keep reading, especially the people that are working at this fringe of machine learning and our traditional mechanical engineering and aerospace disciplines. And just keep experimenting. Don't give up. I have one night every week where I have a few hours to just play. Maybe nothing productive comes out of it, but I'm going to code, play, try new stuff, break stuff. Maybe the night ends with me just deleting the whole thing and being mad because it was such a fail. But I think it's really necessary. And, you'd be surprised at how open source the nature of it is. So therefore, you have a lot of resources to go through and learn and grow essentially on. I think I don't remember the exact numbers, but there was an outlook from Stanford in 2020 on AI, and one of the factoids was open source nature. And I think that something like 20 to 30%, I could be wrong, so don't quote me, but it's 20 to 30% of some of these main journals and conferences did share all of their code. So, there is a tremendous opportunity there that we don't traditionally have in our disciplines of mechanical and aerospace. I mean, people don't normally share things like that. So, yeah, it's, grab a Google Colab account or set up your IDE Python on your machine and just go to town and be intentional to just play with things.
Great conclusion. And also, how do you keep yourself up to date with the plethora of papers coming out? Do you follow specific, I don't know, the Justin guideline, or do you just pick a paper that interests you, or do you follow specific researchers? How do you do it?
It's tough. It's not so easy. Just if you look at how much things compete for our attention in terms of notifications or news sources or information sources over the last 10 years, it's straight up. So it is hard to pick and choose the best ones. But, I certainly have just the things I routinely happen to notice papers on or updates and then go digging and stuff like that. But yeah, just keep going. It may not be a perfect process, but you'll find things and you'll read and you'll learn. You'll find your favorite authors.
Yeah, if you have any links, maybe, yeah, that's true. And maybe if you have a few links, I don't know, to GitHub repos to papers or so, feel free to send them to me and I'll put them in the description of this webinar. It was really nice talking to you, Justin. And yeah, always interesting to see your posts on LinkedIn on what Siemens offers and also what you do with Monolith. So really, really cool. And hope to have you maybe in the second part in the future. Who knows? But yeah, thank you very much for being on my show and talk to you soon.
It was my pleasure. As a closing note, maybe one day someone should interview you because I think you have a lot of really good experience as well that you could share. You probably meet with a lot of amazing guests and have some good answers too. But yeah, thanks for having me. I enjoy listening to your stuff. So it was really cool to be a part of it. Hopefully people get a lot out of it, but always feel free to reach out if you listen to this and want to ask questions, follow up with me directly. I think LinkedIn's pretty easy to reach me, but yeah, don't hesitate to reach out.
Awesome. Have a nice day, Justin. Bye-bye.
You too. Bye.